Okay, so thank you for invitation, and my talk is on categorical data, high-dimensional categorical data. I'm going to show you some algorithm which can work with categorical data, and this algorithm can work efficiently in high-dimensional case. Moreover, I will also show you some theoretical results of this algorithm. My talk is based on the joint work with Szymon Nowakowski and Piotr Pokarowski from University of Warsaw in Poland. Okay, so if you want to stop me or interrupt me, ask any questions, then I think you can do it wherever you want. Generally speaking, in my talk, I will focus on generalized linear models. I think that all of you are familiar with them. However, maybe I will very quickly show you notations and then later few easy examples. So we have some response variables. They are denoted by yi. We have also some vectors of predictors, which are denoted by xi dot. And we assume that these predictors are deterministic. We have also some parameter, true parameter, which is denoted by beta dot. And there is also some function gamma, which is known. And the relation is, as I think you have all seen, that the expectation of your response is the gradient. This notation means the gradient of function gamma. And here we've got the scalar product of predictors and this true parameter. So this is a more or less standard version of generalized linear models. Later I will show you some examples. But what is important is the next slide. In my talk, I will suppose that our vectors of predictors can be divided into R different groups. So for instance, when you consider some gene expression data, then these groups may correspond to gene pathwise, or which is the thing that I will focus on in this talk. The case is that every group corresponds to a factor. So I consider mainly categorical data where I've got some factors, and in such a case, it is quite natural to divide your data into groups. So this is my main goal, to study categorical data. So if this is the case, then let's say I've got R groups, I've got R factors. So every predictor can be written as some subvectors xi1, xi2, xir, where every xik, as I told you, corresponds to the factor. And my notation is quite standard. I mean, let us assume that every factor has levels which are given here. So for instance, k factor has levels 0, 1, 2, 3, up to pk. So the factor number k has pk plus 1 levels. The first level is denoted by 0, and it is called the reference level. And in your data, it is omitted because your data are dummy variables. I mean, for every factor, you have only 0 or 1, and there is 1 if your observation is on on some level. And there is only one exception. I mean, so in these factors, 2, 3, 4, and so on, you do not have a reference level. However, we have reference level in the first factor. This is only to be able to consider the intercept. So there are mainly two possibilities which notation you can use. The first one is that you have explicit intercept and you do not consider any reference levels in your factors. This is not our case. We have decided to use the second notation where you have one reference level in the first factor, which is more or less intercept, and the rest of levels, the rest of reference levels are omitted. And this is our notation. So for instance, if in your data you have some mixture of continuous predictors and factors, then obviously you can as well use this notation. I mean, if your predictor is continuous, then just this is group which has only one element. So this is just one column in your data. So for instance, if you have some factor which is, let's say, race, so you have 3 levels, white, black, and yellow. So in your data, basically you have to use 2 additional columns to be able to code this vector. And if this vector is the first one, then you have to use 3 columns. Okay. So I hope that this notation is clear for you. If no, then maybe I can write something if you have any questions. If not, then I will go to the next slide. Sorry, maybe the last line on this slide. So my vector, every vector of predictors is p-dimensional, where p is 1 plus the sum of pk's. So this is because we've got r factors. Each of them has pk levels. Sorry, pk plus 1 levels. I discard every reference level except the first one. So this is why we've got something like that. Okay, so the similar thing can be done with respect to your parameters. I mean, this is the true parameter. It can be divided into R groups, R subvectors. So each subvector from k equal to 2, 3, 4, and R has pk coefficients. The first one has p1 plus 1 coefficients because the first one corresponds to the intercept. Okay, the next notation is about the error epsilon I, which is the centered response, yi minus the expectation, and we assume that it is sub-Gaussian with some number delta, sigma, which is positive, which means that the moment generating functions can be upper bounded in the following way. So for instance, if your variable is normally distributed with mean 0 and standard deviation sigma, then you have equality here. So this is some a little bit weaker assumption. Maybe not a little bit, just weaker assumption. Okay, so 2 main examples of generalized linear models are the normal linear model. So you have the additive noise, and your function gamma is quadratic. So if you take the derivative, this is identity, and your noise is normally distributed. So obviously it is sub-Gaussian. The second well-known example is the logistic regression. So this is the case, and this is the case where your response variable is binary 0, 1, and the probability of being 1 is given by the following well-known formula. So now your function gamma is just as follows. If you take the derivative, then you have this. You have expectation over 1 plus exponent, and obviously this response variable is bounded, so it is Gaussian as well. Okay, could you tell me if there are any problems with my connection, or everything is fine?
It's fine.
For me, everything is fine.
Oh, okay, thanks. Okay, so these are two examples. So now we go to our problem. So we work with categorical data, and our problem is high dimensional, which means that the number of parameters P can be much larger than the sample size. And I will recall you that P, the number of parameters, is the number of levels in your data, of levels in all factors. Of course, we assume some sparsity we have to assume some sparsity in our data. So I assume that the number of active variables is much smaller than n. And what the active variables mean. In a second, I will show you it formally. However, as I told you, P is the number of all levels. So active variables are distinct levels, because if you have a factor, then possibly some of the levels of this factor can be taken together, can be merged. So, the active variable means that this level is considered after a possible merging. Okay, so generally speaking, there is a very popular algorithm which can work with high-dimensional data, which is lasso. I think you know it well. So this is the penalized log likelihood. So we minimize the log likelihood, negative log likelihood, which is for generalized linear models given by the following formula. So here you've got the linear part, here you've got the nonlinear part, and you add a penalty, which is the L1 norm. However, this is not the good choice, I think, if you work with categorical data, because this estimator treats our dummy variables as separate predictors. I mean, if you apply this estimator to your categorical data, of course you can do something like that. However, if you do it, then every column, when you have 0 and 1s, it will be treated as separate predictors. However, it's clear that you have some structure here. You have some groups which corresponds to factors. So it would be better if we consider such a structure. And to do it, in 2006, some modification of lasso was proposed, which is called the group lasso, and it is about. It is quite similar, however, with one important difference. I mean, previously, in the lasso, there was a penalty, which was the sum over k, the sum over y, and here you've got the L1 norm. Here you have the sum over k, but here you've got the second norm over the whole subvector beta k, which corresponds to your factor. And this is crucial. I mean, maybe first notice that this is not the same penalty as in rich regression, because in rich regression you have square here, and if you have square, then your function is differentiable with respect to beta. But if you have a norm, then it's clear that the norm is not differentiable for the case that beta k is 0. It is a vector which is 0. In such a case, it is not differentiable, and in this way you take into consideration the group structure. I mean, if your parameter lambda k is sufficiently large, then the outcome of this algorithm will have on the coefficients which correspond to the k factor only zeros. So it would give you the opportunity to discard this factor as being irrelevant. Okay, so that is crucial property of this algorithm. So what you also should remember about is if you work with regularization techniques, you should first do some standardization of columns or in some other ways. So here, first, before using the group lasso, you should orthonormalize your groups. I mean, this can be done very quickly because it corresponds only to groups. So you do not have to orthonormalize your whole matrix, which is n by p. You just need to do it within groups. So for every group separately, and it can be done very, very quickly using, for instance, some decomposition like singular value decomposition or something else. Okay, so and in this paper, it was proposed. They proposed some choices of these tuning parameters lambda, which are crucial. And the first choice was to use the same parameter for every factor. The second choice is to use different parameters. This penalty should be multiplied by the square root of pk, where pk is the number of levels in factor. So generally speaking, if your factor is larger, it has a larger number of levels, then your penalty should be larger. And later I will show you that from our results, it looks like this choice is not proper. I mean, this choice is not proper, the second one. The first one seems to look nice. However, the second one looks to be a little bit too large. I will tell you about it later. But what is important, group lasso can only do something which I call the group-wise selection. I mean, it can tell you only which group should be discarded and which group should not be discarded. The group lasso is not able to merge levels of factors. So if you have some group which is significant, then you do not know which levels may be taken together, may be merged. And this is our case, because if you are able to do something like that, then you can very strongly decrease the dimensionality of the problem that you consider. Okay, so here you got some papers about group-wise selection. However, I am not interested in that. So maybe I will go to the case of partition selection. So this is the case where your algorithms can not only discard the whole factors, but they can as well merge levels of these factors. So here you've got some algorithms. So as you can see, recently there have been some interest in that. But to the best of my knowledge, there are only two of them, the DMRNet and Scope, which can work efficiently in the high-dimensional scenario. And there is no theoretical result on the consistency, on the partition consistency for the high-dimensional case. So,
can I just ask you, Wojciech, is scope related? Is it a sort of derivative of slope or some extension?
sorry, could you?
Is scope an extension of slope? Is it? Are they related?
No.
No.
They are not. No.
Okay. Thanks.
So our goal was to propose some algorithm which can work in the high dimensional case efficiently, and the algorithm that we could prove some theoretical result. And this is what I'm going to show. But first, before this theorem, then I will tell you what is a model here. So a model is a sequence of partitions. I mean, you have R groups, you have R factors, and the model looks like the sequence of partition. I'm not sure if you are familiar with this word partition. However, if you have the partition of a set, means that you can divide elements of this set into some parts in such a way that every part is non-empty, they are disjoint, and if you sum them, then you get the whole set. So I think that more or less it is clear. Okay, so this is the model. Of course, every parameter determines a model in the following way. So if you consider only the K partition, the partition which corresponds to the K factor, then there are two possible equalities which may hold or may not hold. So first is, if you have 0 on some level J, then it means that you should merge the level J with the reference level. And if you have on two levels, let's say J1 and J2, you have the same numbers, then it means that you should merge levels J1 and J2. Okay, and it is obviously done separately on every factor. Okay, so this is how every vector determines a model. Okay, so our algorithm is as follows. It is called group lasso merger because it has two steps. The first one is group lasso, and then we use the group lasso to merge levels. So this is something like a modification of group lasso, let's say. So our first step is computing group lasso. So we minimize the function very similar to previously. However, here we put some matrices, some weights. They are diagonal, and on the diagonal they have some numbers which are deterministic and which are positive. So by default we put as these numbers the square root of njk, where njk is just the number of observations that you have on the jth level for the k factor. Okay, so this is our default. However, our theorem works for a general diagonal matrices wk, and what is more, I will try to optimize this choice in some way. Okay, so using this default choice is you can prove that it is, you can show it is not a proof. You can show that it is equivalent to using to use the orthonormalized matrices. Because maybe I will stop for a second here. When you work with factors with categorical data, then it is quite clear, I think, that this matrix is all the time orthogonal. If you consider only such a matrix which corresponds to a group, then if you multiply it, then you have something which is orthogonal. here, so on the diagonal, there might be some non-zeros, and outside the diagonal we have zeros. So here it means that on the diagonal we have ones. Generally speaking, there might be some numbers which are not ones. Okay, so this is quite easy. Okay, and assume that you have your group lasso estimator. Then we are doing merging. We take this estimator, we take some threshold. So assume that this is some number, fixed number. Later I will tell you something about this threshold. So first you discard irrelevant factors, which are 0. You take only significant ones, and you try to merge their levels. I mean, take the factor number k and first check which coordinates are small. In the absolute value, they are smaller than tau. And these values, these levels should be merged with the reference levels. And the remaining levels should be ordered from the least to the greatest. And then you do very easy task. You take 2 consecutive estimators and you check if the difference between them is smaller than twice tau. If this is smaller, then it means that these 2 levels should belong to the same cluster. And that's all. In the proof of the theorem, we confirm that such a rule is enough to find the true model. Okay, so possibly if we for a while forget about categorical data and go back to continuous predictors, then I think you are familiar with an estimator which is called thresholded lasso, which is first calculating the lasso, and then you check which coordinates in the absolute value are smaller than some threshold. If they are smaller, then it means that they are irrelevant. They can be discarded. So our algorithm GLAMER is a simple extension of this approach to categorical data. I mean, here we do not discard only those which are small, but if they are close to each other, then they are merged, they are taken together. So this is some extension of this thresholded approach to categorical data. And now I'm going to show you the main theoretical result, which bases on something which is called cone invertibility factor, which is quite standard when you work with lasso estimators. Maybe it is not so nice. It looks a little bit difficult, so I will show you it. However, I think I don't have so much time to go into details, so I will just show you it. So first we have a set of active groups. I mean, these are they correspond to those factors which are relevant. So obviously this set need not coincide with the true model, because here you might have some merging of levels. Here you do not have any merging. And in the definition of this cone invertibility factor, you need some cone, which definitions looks like that. If you go back to continuous predictors, then this is exactly the same as previously. So I will go to the cone invertibility factor, which is some measure of degree of separation between the true model and some other models. I think maybe this definition looks quite not nice. However, for instance, if your model is linear, then it looks much better. I mean, here in the numerator, you got something like that. So, for instance, if your data are orthogonal, you can very easily calculate. Sorry?
So actually, I didn't hear what you say. Oh, okay. No, it's okay.
Okay. I mean that if your model is linear and orthogonal, then you can quite easily calculate it. Obviously, it depends on this matrix W, which is diagonal, and on the diagonal you have these matrices, smaller matrices W1, WR. However, if if this is fixed, then you can quite easily calculate for the orthogonal case. Okay, and the theorem looks like that. So we have sub-Gaussian generalized linear models. We have two numbers from the interval 0, 1, A and alpha. We have some new object, which is NW. This is the maximum over the square root of number of observations on the Jth level, K factor, by WK. So now we consider general case. So this matrices W can be general. If you take your tuning parameter as follows, here we've got the sigma squared, here we've got n squared W, here we've got the logarithm of P as usual. Then you can prove that with high probability, if your alpha is small, then this probability is close to 1. Your estimation error, the difference between group plus SU and your true parameter in the infinity norm is smaller than some number times the tuning parameter times the inverse of cone invertibility factor of this guy. Okay, so this is the main result. So notice that if you take the default case, as we did in the algorithm, so if you take this W as the square root, then you have 1 here. So NW is just 1, and your lambda parameter is, as usual, the sigma squared times logarithm of P, more or less, logarithm of P of the number of parameters in your model. So this results is an analog, strict analog of estimation consistency for standard lasso. By using the name standard lasso, I mean the lasso which works with continuous predictors. Okay, so this is the main results. And of course, there are plenty of similar results in literature on the group lasso. Generally speaking, they use some mixtures of norms. So for instance, here we've got the maximum over K, maximum over J. They have maximum over K, but here they do not have infinity norm, but the second norm, and they bound it by something. So for instance, in these papers, you can find something like that. So the main remark is that we measure this estimation error in the infinity norm. So here we've got infinity norm, and here. So our object that we want to bound is smaller than this guy. This is why we can obtain something smaller on the right hand side as well. And in fact, the L infinity norm, so maximum, and here infinity norm in the place of the second norm, it is all we need. So this is why using our result, you obtain something better in the sense that your assumptions are weaker. Later, I will show you an example of that. Okay, so we have estimation consistency. So there is only a little step to prove partition selection consistency. All you need more is something which is very similar to the beta-mean condition in continuous predictors. When you work with continuous predictors, you have to assume that the smallest signal you have is sufficiently distinct from 0. here you have to prove that these levels for particular factors are sufficiently distinct. Okay, so this is the only difference. So we do it separately for every factor, and the difference between true levels, two true distinct levels should be large enough. Okay, so now for the GLAMER, if you have your threshold between this guy and between this, then GLAMER is able to find the true model with high probability. So, so this is some confirmation of theoretical properties of this estimator. So as you can see, GLAMER is a generalization of thresholded loss, which is used for continuous predictors. Here we generalize it to partition selection. But there are two. As I told you, I think it is the first result on partition selection for high dimensions. So, and what is more, there are two questions. First, how to choose this threshold. This is the standard problem. We cannot do it from this theorem because these two endpoints, the left endpoint and the right one, are unknown. They depend on the true model. For instance, this depends on the true model. This guy also depends generally on the true model. So, so later I will show you how we do it in practice. We do it using some information criteria. And the second point is how to choose weights. I mean, if you forget about this guy in the middle, the threshold, then it means that your, let's say, beta mean condition, this guy has to be sufficiently large. And here you have some dependence on weights, because psi depends on weights W, but lambda as well depends on this choice of weights. So the second question is how to choose weights, and we tried to answer this question, however, only in some restricted scenario. I mean, so first, I recall you that this is the NW, and sufficient condition, this condition, if you take it in the simplified form, then it looks like that. There is some constant. There is this number which depends on weights, the second number which depends on weights, and the logarithm of p. So if you want to find optimal weights, you should minimize this guy with respect to the weights. And as I told you, this is quite difficult, because generally speaking, it is difficult to calculate this cone invertibility factor. But we tried to solve this problem in a very restricted scenario. I mean, we consider only the linear model and only the case where your matrix is orthogonal, globally orthogonal. And what is more, we also assumed that your weights has such a form where Q can be any number. So the question was how to find Q, which gives you the best weights W. And in this restricted case, you can do it quite easily. If you have two numbers, n small m, which is the minimum number of observations per level, and n capital M, which is the maximum number, then you have then you can easily prove that this guy, which I am interested in, is smaller than this guy. And here you've got, in the bracket, you have some number which is greater than 1, greater or equal. This is maximum of something, this is minimum of something. Maximum is always larger. So if you want to minimize this guy, then here you have some exponent which is non-negative, so it should be 0. you can easily prove that it is 0 when your number q is between 1 and 2. So in such a case, you can easily solve this problem. So every weight with q between 1 and 2 gives you the optimal weights. So if you do it like I have said a second ago, then your sufficient condition for GLAMER looks like that. Okay. So now I will compare this result with the seminal paper of Yuan Lin when the group lasso was defined. So first, let's take this left endpoint and right endpoint. So it is quite easy. If q is 1, then you have just the square root. If q is 2, then you have the number njk. So the first choice, q equal to 1, strictly corresponds, it is equivalent to this first choice in Yuan Lin. However, the second choice, which was given in Yuan Lin, was they told us to multiply the penalty by the square root of pk. If you consider the balance design, which is a little bit more regular, I mean, the number of observations per level is more or less similar for each levels of a factor. It is just n divided by pk. So if this balance, your design is balanced in such a way, then the second choice, this choice, which seems to be optimal in our case, corresponds to the following penalty. So as you can see here, we do not have multiplication, but we have division by the square root of pk. And if you think for a while about this problem, then obviously the second norm is the square root of sum of squares. So we propose to take the square root of sum of squares by the number of summands. So we should, in our result, it seems that we should average. However, in their result, it looks like we should to multiply, which is quite strange, I would think. However, of course, we did it in the restricted scenario, and I think we should also make some experiments where we compare these two choices. However, this is just to inform you that it seems to be a little bit different in theory than in practice that they proposed. Okay, so I think I do not have much time now, so maybe I will skip the few slides. So it was the sufficient condition, but we have also compared it to the necessary condition for the partition selection, and the necessary looks like that. So obviously we have larger constants. Here we've got 128, here we've got 1 second, but log p is exactly the same, and the second difference is that here we've got n capital M, so this is the maximum number per level. The inverse, here we've got the minimum number per level. But if you're, so one could ask, is it possible that these two conditions are similar with respect to constants? And if your design is regular, I mean, for instance, if it is balanced and if the maximum number of levels is similar to the minimum number of levels among each factors, then these two guys would be very close to each other, of course, with respect to the constants. Okay, I think this was the last theoretical slide. So now maybe I do not have much time, so I will try to briefly tell you about experiments. So first, in the theoretical results, we consider only one parameter, only one tuning parameter lambda. In the practice, it is much better to use many lambdas. I mean, to take a grid, to take many lambdas. It is from the computational point of view, it is quite easy because there are some implementations of group lasso which can do it efficiently. So we did it. We take lambda from a grid, and for each particular lambda, we calculate the group lasso. Then, as I told you, we are not able to merge using this threshold because we do not know threshold. So we replace this step by clustering, which is about trying to find the nested family of models, and then finally, when we do clustering, the similarity measure is based on this group lasso, and then finally you have some family of models, and you can find the final model using cross-validation or using the information criteria. And we also have the second algorithm, which is very close to this GLAMER. In fact, the difference is in this second point in the first step. I mean, here we use the clustering on the basis of this similarity measure given by group lasso. However, the group lasso might be biased, so maybe it is better to refit your estimator, and DMRNet does something like that. It once again computes the maximum likelihood, and generally speaking, it gives better results. So these are our two algorithms. However, we do not have any theoretical results on the DMRNet. We are working on that. But from the practical perspective, we can use it. Sorry. So we have 4 data sets. 2 of them are with continuous responses, not continuous predictors. Predictors are categorical, but responses are continuous. And here you've got 2 data sets with binary responses. So this is the sample size. This is the number of parameters. So as you can see, maybe these data are not so high dimensional. And here you have a P which is larger than N. Okay, I will show you. So we have also some simulation results. However, I do not have them here. So there are 7 algorithms: lasso, group MCP, and 3 algorithms which are able to merge levels: scope, DMRNet, and GLAMER. And we compare predictive error denoted by PE and model dimension denoted by MD. So this is the first slide with results for the first data set. Here you've got the prediction error on the left. On the right, you've got the model dimension. And here you've got estimators. So this is GLAMER with cross-validation, GLAMER with information criterion, DMRNet with cross-validation, with DMRNet with information criterion. This is scope with some parameter, another scope. This is group MCP, group lasso, and lasso. And here is model dimension and the same estimators. So as you can see, these 3 estimators, which are not able to merge levels. So in prediction, they are quite nice. However, if you try to look on the model dimension of them, then it is quite large. It is larger than here, somewhere there. So they are able to predict quite nice. However, from for instance, the interpretability point of view, they are useless. The number of parameters they use, the model dimension they use is very large. However, our estimators, which can merge predictors, merge levels, in prediction, they are pretty the same. However, as you can see from the interpretability point of view, they are much easier. For instance, here you have 9 distinct levels. Here you have only 6 distinct levels. Here, as you can see, there is some problem with scope. It is possibly it loses some significant levels because its predictive errors is quite large. Okay, on the second slide, it looks pretty the same. These 3 estimators can predict in a nice way. We are not much worse. However, our models are much smaller than those models. And here you have classification problems. So as you can see, it looks pretty the same. And finally, here I've got some references. Okay, so thank you. That's all I wanted to show you.